So what we want to do here is we're looking to kind of come up with a formula for the kth term of a binomial, right? When I refer to a binomial, I mean something like these three examples that I've got here. It's a binomial raised to some power. And what I want to do is I want to come up with a formula um, to describe what the coefficients of each term are. All right, so what I've done here is I've written these out, right? And with the first one, you can really follow what I did. I used the old FOIL method, right? A plus A is A squared. Then what do we get? We get A times B, we get B times A, and we get B times B. That's B squared. Okay, so what I want you to notice here is I have here in the middle both possible arrangements of A and B, right? I could have the A first and the B second, or the B first and the A second. And of course, now you can combine those two because they're like terms, and you get A squared plus 2AB plus B squared. All right, so now I did the same thing down here. Right, I did the same thing with A plus B cubed. And didn't want to make you sit here and watch while I wrote out all of these. Obviously, they get long really quickly. You're welcome to write these out for yourself and confirm that I did them correctly. But what do we have here? We have, that's going to be the A cubed term. That's going to be the B cubed term. Now look at these three here. Those three are going to make up our A squared B term. And because there's three of them, we're going to end up with 3A squared B. These three here all simplify to AB squared. And again, there are three of them. So we're going to end up with 3AB squared. And again, we're thinking about this combinatorially, right? How many different ways can you choose? How many different positions could you choose to put the A's? Right, I'm looking at this first one. I have 3 spots here. I have to choose 2 of them to get the A's, right? And then the remaining one is going to get the B's. So if you look at 3, choose 2, that comes out to 3. And then what do I have here with the AB squared? Well, now I have 3 positions again, right? And I have to choose one of them to get the A, and then the remaining 2 will get the B. So how many ways can I do that? Well, it's 3 choose 1, which is also 3. Okay, so hopefully, based on those two, you see a pattern, right? How about the B cubed one? Well, here I have 3 places, and I'm going to choose 0 of them to get the A's because there's no A in that term. Well, 3 choose 0 is 1. And how about the first one? Here I have 3 positions, and I have to choose all 3 of them to get an A. 3 choose 3, that's also 1. Right, so if I finish this out, right, put the A cubed here and the B cubed here, you notice the coefficients exactly match those combinations. Right, so let's try one more time. Right, I did one more here with A plus B to the 4th. Right, so if we start off with the A to the 4th term, the next term is going to be A cubed B. So that is this one, this one, this one, and this one. Right, so we're thinking about positioning the A's, right? I have 4 spots in each of these products to choose from. I need to pick 3 of them to get an A. That's 4 choose 3, which is 4. And yeah, look at that. That's exactly how many we have there. Right, now, how about the next one? Right, this is the A squared B squared term. 1, 2, 3, 4, 5. There's 6 of them. Was this following the pattern? Well, I have 4 slots to fill. I get to choose 2 of them to get an A. 4 choose 2 is 6. Worked again. Finally, well, not quite finally, we've got these, right? These are the B cubed A. 4 places. I'm going to choose 1 to get an A. That's 4. Again, this one is 4, choose 0, because there's 0 A's going in there. That's 1. This is 4, choose 4, which is also 1. You're starting to see a pattern, right? You're starting to see a pattern, hopefully. But I want to point something else to you here before we go any further. I'm going to just pull out these coefficients, right? The A plus B squared was 1, 2, 1. Sorry, let me write that a little further over. We need a little more room than that. 1, 2, 1. The B cubed was 1, 3, 3, 1. And the A plus B to the 4th was 1, 4, 6, 4, 1. Hopefully, if you watched the last lecture, if you remember the last lecture, hopefully this looks really familiar, right? Because the numbers that I'm getting here, where 1 plus 2 is 3, 2 plus 1 is 3, 3 plus C is 6. These are exactly the numbers that we saw when we were writing out Pascal's triangle. Right? That's the connection back. That's why we talked about that first in the previous section. Okay, so what I've done here is I've written this out just in the most general terms. If I want to multiply out A plus B to the n, right? Then there's n plus 1 terms, remember, because we start counting at 0, right? So the polynomial is the sum k equals 0 to n. I want to emphasize something here. K is a constant. Excuse me, n is a constant. And n is the degree of the polynomial. 4, 3, and 2 in the last examples that I looked at. Right? So this number here and this number here is going to be fixed. Then what we're doing is we're letting k equals 0 to 1. So this is going to be n choose 0, n choose 1, n choose 2, n choose 3, and so on, which if you look back at what we did on the last slide, you'll see that that is exactly what the combinations that I wrote in there were doing. Right? And then here, the exponents, right? The A one, remember, k starts at 0. So this starts out at n minus 0, which is n. Then it goes to n minus 1, n minus 2, and it just starts walking its way down. Right? So it starts a to the 4th, then a to the next term has an a to the 3rd, a to the squared, and so on. And the b's are going in reverse. The b's are b to the k, so that starts at 0, then goes 1, 2, 3, 4, 5, all the way up to n. Okay, so how can we prove this? Well, there's an algebraic proof of this, and it's very long. It's very long and really not very pleasant. This is a case where the combinatoric proof is much, much simpler. Okay, so all you're doing is we're going to repeat the argument that we kind of saw with specific examples on the previous page. Look at any given term, right? Pick a n minus k, b to the k. And I want to know what is the coefficient of this. Right? Well, this term is made up of n minus k a's and k b's. Okay, so I know that when I'm multiplying this out, I'm going to see all of the possible arrangements of these elements, right? All the possible arrangements of a's and b's. So how many places do I have here? Well, I have n minus k plus k. That's just n. Right? So I have n spaces, if you will. And to get all of the possible arrangements, I have to choose k of them to have the b's. Right? How many ways are there to do that? Well, it's n choose k. Each one of those ultimately is going to be a like term. So when I add them all together, the coefficient is going to be n choose k. It's going to be a n minus k b to the n. And that's exactly what the formula is saying is each individual term. Okay, now there was a small assumption that I made, and that was kind of buried in here. Okay, when I did this, I am by saying we're going to count the number of ways. that numerator really needs to be greater than 0, right? So I kind of quietly made the assumption here that n is greater than or equal to 1. Okay, but what if it isn't? Well, let me get a clean slide here. If n is 0, then this really is pretty straightforward, right? If n is 0, then the left side is a plus b to the 0, which is just 1. Okay, what happens on the right-hand side? Well, this is the sum k equals 0 to 0 of 0 choose k to the a, make sure I get these right, a to the negative k, b to the k. Okay, which maybe looks a little weird, but k is going from 0 to 0. There's only one value k takes on in this whole thing, and that's 0. So this is 0 choose 0, a to the 0, b to the 0, 0 choose 0. Okay, yeah, that's pretty weird, but it's 0 factorial over 0 factorial times 0 minus 0 factorial. A to the 0 is 1, b to the 0 is 1, 0 factorial is 1. So yeah, in the special case that n is equal to 0, the left and right sides, they both come out to 1, and the formula does still work. Okay, now we've got the formula, and it really is a very elegant formula. If you're trying to write a computer program to do this, it's just one loop. It really is very straightforward to write. But what we're going to do in the next lecture in this series, we're going to look at some specific examples, right, and see how that formula is used to actually work out some specific polynomial expansions.